Hi Noah. Great question about the rate laws. So it's just too hard for me to type in an email, so I'm going to do a few examples for you here by hand. So when the slow step or the rate determining step is the first step of your mechanism, it's really straightforward. It's just the rate law for that step will be the rate law overall. So for this one, the rate law would simply be rate equals small k for the rate constant times the concentration of NO2 squared, because there's two of them. Okay, and that's all you need to do and you're done. When the slow step is farther down in the mechanism, you have to include all the steps up to and including the slow step. So you can't just look at that. And here's why. So here's this, in this second one, this is my rate determining step, which means my rate law would be rate equals small k concentration of N2O2 times the concentration of H2. And this isn't wrong. That is the rate law for the rate determining step, but it's not best practice to put an intermediate in a rate law. Because if you're trying to control the rate of this reaction, you want to know what do you have to do to the reactants. And the only reactants are NO and H2 in the overall equation. N2O2 isn't something that the chemist can add to the reaction vessel because it's produced and then consumed. It's an intermediate. So if you can get rid of that, you want to. And there's a long way involving math that the guy would have showed you in the YouTube video, and then there's a shortcut. So I'm going to do the long way first and then go back and show you the shortcut. All right, so long way is the first step is almost always at equilibrium, you'll notice in these problems, and that has to be so for this to work. If this is an equilibrium and we assume it reaches equilibrium, we can say the forward rate equals the backward rate. So I can say rate forward for the first step equals rate backwards for the first step, which means K forward times the concentration of NO squared, because there's two of them, equals K backward times the concentration of N2O2. So I'm just writing the rate law for that step going forwards, the rate law for that step going backwards, and setting them equal to each other. Then I can use algebra to rearrange this to get something to sub in for N2O2. I'm trying to get rid of that intermediate. So let's solve for N2O2, and we end up with K forward divided by K backward times NO squared. All right, so I'm going to take this entire expression and sub in to get rid of N2O2. And that leaves me with rate equals K times K forward over K backward times NO squared times H2. When you have a constant times a constant over a constant, you can just say all of these equals some new constant. Let's call it K2. Okay, so rate equals K2, it doesn't matter, it's some rate constant, times NO squared times H2, and voila, we got rid of the intermediate. Now we have a rate law that's just in terms of reactants. Okay. I'm going to do this 2 more times just so that you can get a sense of the algebra. Then I'm going to go back and show you the shortcut. So here's the next one. You'll notice NO is a really common one for these. So NO reacts with Br2 in equilibrium, but it's fast. The slow or rate determining step doesn't come till later in the mechanism here. So this is my rate determining step. Let's write a rate law. K NOBR2, there's one of them, and NO is one of them. That's fine, it's correct, but it's not best practice because this NOBR2 is an intermediate. So I want to try to get rid of it. Let's go back up to the step before. Assume that the forward rate equals the backward rate. I can then do exactly what I did above. There's the rate law for the forward step. Set it equal to the rate law for the backward step. Solve for the intermediate I'm trying to replace. And then do my substitution. So rate equals, and I'm just going to go ahead and say k times kf over kb equals some new k, some new constant, times NO times BR2 times NO again, which means really it's k NO squared BR2. So we've got second order with respect to NO and first order with BR2. Before I do the third one, actually, let me just show you the shortcut. So if you look at these two that I just did, what you might notice is that what's happened is it just includes everything, all the reactants, up to and including the slow steps. Let me show you what I mean by that. For this one, stop at the slow step. If I cancel this intermediate and I say that's produced and then consumed, all that's left is 2 NOs and an H2. And if you look at your rate law, it has 2 NOs and an H2. That's it. So you actually don't even have to bother with all this math. If you can cancel the intermediate, then anything that's left on the reactants side is in your rate law. Let's do the next one. Up to the slow step, I can cancel this intermediate. That leaves me with an NO, a BR2, and an NO. And look at my rate law. It's got an NO, another NO, and a BR2. Okay, so that's actually much easier than it looks. You don't have to go through all the math. Now, there is a caveat, which is the one I've got on the back here. So I'm going to do the long way. Then we're going to go back and explain how the shortcut needs to be tweaked, or you need to be careful with the shortcut if you get one like this. All right, so we go up to our slow step. Let's write our rate law. This one has 1 atom of chlorine and a molecule CH3Cl. Okay, the atom of chlorine is my intermediate that I want to get rid of. So let's do the top one. Rate forward, it's equilibrium, so rate forward equals rate backwards. K forward times Cl2, there's my forward one. And K backward times Cl atoms squared. There's my backward. Solve for Cl. So Cl squared equals K forward divided by K backward times Cl2. Okay, hopefully you've realized we have a problem. Our rate law only has 1 chlorine atom, but this has chlorine squared. So I need to do the square root of both sides. When I do that, I can get an expression for Cl. It's the square root of Kf over Kb. That's no big deal because that's just a constant. But Cl2 ends up square rooted, or I'm just going to say to the half power. And when I sub all this in, just like I did on the previous page, I get rate equals K times the square root of Kf over Kb. Again, that's no big deal because we're just going to say that's some new constant. Then Cl2 to the half CH3Cl. I think this one actually was on the rates test. If Mr. Beaumont gave you my rates test, this should have been the last question. Because it's one that trips people up. They don't realize you can have unexpected orders. It doesn't have to be the first or second order. You can have a half order. You can have a 3/2 order. You can actually have a -1/2 order. That's something that slows a rate down. So don't be intimidated if you see that. It does exist. So my final rate law is K, or K2 if you want to say, Cl2 to the half CH3Cl. That is your final answer. Okay. So let's go to the shortcut now. Remember, in the shortcut, we canceled intermediates, and then we circled what was left. Okay. If I want to cancel the chlorine, I have an issue. We have 2 chlorines up here. That means only half of this reaction was needed in order for the second step to proceed. And that does actually make sense. Look, you made 2 chlorine atoms, but you only used one of them in the slow step. The next one wasn't needed until way down here. So what we need to do is divide this by half. And then imagine the rest of this is sort of happening down here. Half of a Cl2 turning into the other Cl. So you're using the first half of it for the second step, you're using the second half of it for the third step, which means now I can cancel. Now I can cancel chlorine and chlorine, and I'm left with half of a Cl2, and I'm left with a CH3Cl, which, of course, matches our rate law. Okay? So I hope that was helpful. Do I think you're going to get one this hard? Obviously, it would be doubtful, but if they're trying to distinguish between the very best students, this is the hardest one they could give you, so they might want to trick you out. So at least you've seen it, and you know what to expect there. If you have any questions, feel free to send me an email, and hopefully I can help you out.